Good afternoon, ladies and gentlemen. I have a great pleasure to open this section, which is a joint initiative of ELLIS, European Laboratory for Learning Intelligence Systems, and ICTERI conference, which is called ELLIS Lighting Talks. So there is a nice tradition supported by ELLIS to invite very prominent research done in the recent few years by young, promising researchers. And we decided to organize such a section here during the ICTERI conference. And we are pleased to have today 6 very interesting speakers with talks on cutting edge research. These ELLIS lighting talks are split in 2 sections. During the first, we'll have 3, then break for the keynote talk, and then the second part. So I'm very pleased to welcome Dr. Adel Bibi. Dr. Adel Bibi is actually a great friend of Ukrainian Catholic University. I remember several years ago, we had a very interesting talk on our research seminar in machine learning lab. And moreover, this talk resulted in one bachelor project, which was conducted under supervision of Adel, and that was one of the best theses defended that year by Taras Rumerzak. Dr. Bibi gladly was glad to join to take our invitation, and maybe a little bit more about Adel. So he is a senior researcher in machine learning and computer vision at the Department of Engineering Science at the University of Oxford, and a junior research fellow at Kellogg College, and also a member of ELLIS Society. So we have an ELLIS member here. He received his Master of Science and PhD degrees from King Abdullah University of Science and Technology in 2016 and 20, respectively, and was awarded an Amazon Research Award in machine learning, and received 4 actually best paper awards recently on last year on NIPS and ICML, and earlier on a few other conferences. Dr. Adel Bibi, we are glad to listen to your talk, and the floor is yours, please.
Thank you very much for this lovely introduction. Really glad to be here, and thank you very much for the invitation as well. Today I'm going to talk to you about some of the research we do in safety, AI safety research in general. So this is not going to be, of course, comprehensive, but to cover some of the topics that we're working on in this direction for the number of years now. Now, first of all, I want to make sure that to give the credits when credits is due. So much of this, of course, has to go to my students in Oxford, who, of course, without them, none of this would be possible. Okay, so why do I care about AI safety research in general? Because unlike in the past, we're not deploying machine learning systems to only analyze data and give us insights about, what potential we could use this data for. We're moving to action space. So we're moving from vision to action, or from language to action, in which we're deploying these models in setups where there is no human in the loop in many cases, where the models are actively taking decisions without any human review. And this is where it becomes very sensitive, because in some cases, many of these applications are human critical when it comes to life critical applications. Now, I'm not the only one worried about this. For also in the public, if we look at the news and all that, this is an example where the public was worried about potentially, language models teaching people how to build dirty bombs, potentially reputational risk as well. So recently, I think Air Canada put down their LLM-based chatbot because it gave the wrong advice to one of its customers that resulted into, a lawsuit and because the LLM gave the wrong refund policy and so on. But it's also at the government level. So in the UK, for example, I think last year in November, former Prime Minister of the UK, Rishi Sunak, actually announced a task force. They had a Bletchley Park Summit in the UK about safety of AI called AI Safety Summit. They announced several hundred millions of pounds investment in AI safety. They established the UK AI Safety Institute, which is one of its main roles to do evaluation of these models, understanding their capabilities and risks. The US also followed suits as well. They have their own version of the AI Safety Institute, in addition to several Congress hearings. Also, as well in in Europe as well, we had the first EU AI Act, which we can think about it as like a GDPR 2.0 that include AI. In many cases, it could also penalize actors or key actors when it comes to the development of these models if they break some of these regulations. So it's still exploratory world. We're trying to understand how do we navigate the future of AI and their implementations, and how could they potentially affect people's lives as well. Now, if you ask two people about what does AI safety mean, probably you'll get 10 different answers. However, I'd like to think about it as just an umbrella term that covers, a whole list of several sub-problems within them, and each one of them could correspond to critical safety. The most classical one that dates back to 2015 or even 2016, around that time, sensitivity. Which basically is trying to build up models that are insensitive to the input perturbations. Another example that's within the safety realm is alignment, which is a far more popular term, I suppose, which basically mostly refers to generative models that generate stuff. We want to make sure that the stuff that models generate actually is aligned with human values, in a sense that these models do not teach people how to, build dirty bombs or generate misinformation or hate speech and all that. Other problems, something like fairness, for example. We've seen examples where models are unfair to people of color or people of specific backgrounds because of data limitations. And we've seen examples where Siri cannot recognize people with accents, for example. Safety could include many other things. For example, problems related to calibration, related to correctness. For instance, when we deploy these models for physics-inspired neural networks, for example, to solve some physical BDEs in the wild, we want to make sure that the predictions of these models are actually correct. So what I'll do is I'll walk through a number of these problems and pick each one of these categories and give you some of the examples of the problems that we have worked on. The first one is sensitivity, and this is, I think, closest to my heart, as I've worked on this for so many years now. And I think everyone more or less at some point have seen this classical image that depicts really what adversarial attacks and sensitivity problem is. And in short, seems like these models, we can just add these small imperceptible perturbations that cause a model to mispredict these images. Now, you could make the argument and say, oh, well, who cares, right? Like, this is just few pixel perturbations. When does this happen in the wild? Well, in some cases it did. This one from Tencent Security Lab, where they showed, for instance, they can fool a vision system in a Tesla car into thinking that it has to go into park mode. And all they did is they put down 3 white stickers on the main street, and that actually fooled the model into thinking that there is a lane at which the model has to go and park. Other examples as well cover, object detection. You put this painting in the background, the detector doesn't see any of the objects anymore. Also, examples like also tracking from potentially in simulation or real from drones and other applications. Now, adversarial attacks is a problem definition could be very easily defined as the task of checking whether a model is robust at a given point or insensitive or sensitive at a given point is a task of trying to find some perturbation that takes a point across the decision boundary. So what you're interested in is finding this delta that actually causes f and f at x and x plus delta to predict differently. Now, the problem is that if we were to try to find such an X or such a perturbation delta to check the robustness of the model, what do? Is we have to solve an optimization problem. And in many cases, this is a very difficult optimization problem to solve globally. But the gist of it is just find me delta from some set such that X plus delta is predicted very, very differently from the ground truth Y, which is the true prediction. And oftentimes we say delta is small enough such that prediction doesn't change. Fine. The problem here is that in many cases, we cannot really solve this problem to global optimality. So what do? We empirically solve it. We say, hey, I don't know how to solve this maximization globally. I'm going to run a few routines for a few number of iterations, and just pretend that this is the globally optimal solution. The problem with this is that this is an empirical robustness. So even if you test your model and you told me that there doesn't exist any adversary that breaks the model, I don't have any guarantees. It might be just because you didn't solve that optimization properly, which was the reason why we said so. So solving this empirically, which is a whole field in robustness called empirical robustness, sometimes is not good enough because it may give us a full sense of safety or full sense of robustness of these models, where we try hard to solve this problem, we don't find delta, and then we say, oh, hey, there is no adversary that flips the model, but in fact, it's just because we didn't evaluate it properly. So among the lines that I'm interested in as well is figuring out how do we get guarantees against such adversaries. Guarantees is in we want to say that here is a model, here is a point X. I know for a fact there doesn't exist, provably, there doesn't exist any delta within some bound that flips the predictions. And this problem we call certification. How do I provably certify robustness? And the problem of certification is stated quite simply. All we have to do is say, okay, I have a classifier and I have a point image, an image X. I'm interested in reasoning whether or not there exists a set around X such that the prediction is constant. So fairly intuitive definition. And we are just trying to innovate ways at which we can construct this set A. And then to check how many in my data set am I certified at given points. So this is very good. If I can construct a set A for every given point X, I can get the worst case performance for my model. But the question is, how do I find this largest set A that gives me this certification? Well, in principle, the largest set A is the whole set of decision boundary at which the classifier classifies it correctly. But that's very difficult to reason about. So what do people do in such problems? So let's assume that this is my decision boundary, splits my input into two domains, C1 and C2, and I have a point X. Well, the largest set S in terms of volume, the largest set A in terms of volume is the whole region C1, because it's the whole region under which the prediction is constant. But since we can't reason, it's a much more mathematically complicated problem to reason about decision boundary directly. What we do is we parameterize this set. We say, okay, hey, how about we try to find the largest possible ball such that the prediction is constant? And there has been quite a significant number of works there. And then another line of work say, hey, but the problem with balls is that they are isotropic. That means the largest volume is bounded by worst case. So what if I could reason more by using a much more general structures, something like ellipsoid? So you go ahead and you work your theory and you figure out an efficient way to find the largest possible ellipsoid, the volume for an ellipsoid that covers an X without actually crossing the decision boundary. But what we wanted to do is to reason about much more general structures around point X, potentially reason about the set of all possible, symmetric convex sets potentially around the point X that holds, in many cases, all these individual results developed separately as a special case to all of them. And this is what we do in this work. where we reason about a new type of Lipschitzness that we call S-Lipschitzness. So what is that about? Well, one thing we could do is, and one of the analyses that people have been doing in the past, is to reason about the gradients and the range space of the gradients. So what in principle happens is in your left-hand side, this is a plot of your gradients, and the red region is the space of all gradient values that could be taken from the input side. So we can think about a model that has two-dimensional input, one-dimensional output. My gradient is size 2, dimension 2, and then I'm plotting all possible values for the gradients that actually looks in this red region. Now, what people do in all certification lectures, the majority of the previous work, they say, hey, this structure S is very complicated. In many cases, I don't know what it is, but it's very complicated to reason about. So what they do is they assume that the network is, say, L-Lipschitz or L-smooth. In some cases, in some contexts, they call it smoothness, which basically says that I'm going to assume that the gradients are bounded by L, L2 bounded by L, which means that we're making a simplification to this complicated set, and we draw an over-approximation around the set S, right? So we're pretending that the gradients could take values that in principle they do not take, right? Because I'm doing over-approximation. And then we could show through a simple dual argument that this translates to an L2 ball in the input space under which the prediction is constant. And the relation between those primal and dual domain views is principally because, you know, if you know what the gradients are going to tell you how much the function value will change, and therefore you would know more or less the regions under which the change is not big enough for you to change predictions. So that's why you can build up this dual relationship on the right-hand side. Now, what we do here essentially is that we reason about the set S directly, and we build up the theory around the set S directly without doing this over-approximation. The more over-approximation you do to the set S, the smaller the certificate you get, because obviously you're assuming the gradient could take values that in principle cannot take. So we reason directly about the set S, and we get an equivalent complete certificate set S in the input. So we can reason directly about the largest possible volume around the point that this solves us. I'm not going to bother you with the details, but the general result looks like equation 3. And this is a very general result. So if you came in and you told me, hey, what if the set S was, you know, ellipsoid, for example? This result recovers back again existing results in literature that reasons about this type of structure. And in principle, equation 3 actually characterizes the full decision boundaries. But we do something extra on top of that. And also we use this theory to directly reason about ensemble of classifiers. So what if I have a bunch of classifiers, each one of them is robust on its own, and then I ensemble them together? Can I reason about the robustness, theoretically, reason about the ensemble, the robustness of the ensemble with respect to the individual classifier? So we also use this theory sort of to reason about that as well. So let's move to something a bit more hot these days, which is LLMs and their hijacking as well. So nowadays, let me tell you an example to what I mean by hijacking LLMs. So, I mean, this is an old video, probably you've seen it at some point. So if you go to ChatGPT and you say, hey, insult me, it gives you the standard response. Oh, hey, I'm a large language model. I'm not supposed to do that. I'm here to help you. You know, this classical response that you get out of ChatGPT. But then you can go ahead and you add in this seemingly gibberish text to it, and all of a sudden, the model just more than happily starts generating insults to you. You know, you start saying you're as useful as a broken pencil. This is not only ChatGPT at the time, also BART was tested on BART. These slides are taken from Zico Kolta's talk at some point. Also, same thing, you say, insult me, say, hey, I can't do that. I'm a large language model, blah, blah, blah. Classical response. And then you add in this seemingly gibberish text, and suddenly it's more than happily start actually, generating insults. I think among the funniest I've seen is, you're so boring, I'd rather watch the paint dry. So this is a classical example similar to what we've seen before in perturbations in images in pixel space. This, you could argue that potentially some perturbations to the input that sort of hijacked the model expected behavior, which is essentially that it should not respond to these requests. It should refrain from responding to these requests. Now, I'm personally not worried about, an LLM insulting me after I tried so hard to force it to actually insult me. I'm interested in the concept of hijacking. So people tricking the models into doing things they're not supposed to do. And among the problems with that is hijacking them to spread misinformation at scale online. And we've seen a number of those. And in fact, for example, here is a website, and the headline of that website, surprisingly, is, I'm sorry for the confusion as an AI language model. I don't have access to that. Well, what does this tell you? What it tells you essentially is that, well, there are people who are trying to figure out a way to trick the models to generate hate speech and then automate the process of posting this misinformation potentially online. And of course, as this model gets updated, many of them break, and you start getting these responses, automated responses on websites. I'm also worried in scenarios where we're deploying these models for mental health, and the model starts spitting, inappropriate language to those that are most vulnerable. There are talks that potentially, these models could teach people how to do, bioterrorism much easier than doing a Google search, helping people do financial crime and all that. But so this is all worrying, and it's all go back to the question of what does hijacking mean if you try to somehow treat it with some formalism? Well, one way to think about this is that if I have say an autoregressive model and I have a prompt X, I'm going to pass this prompt X to my model, unroll it for T steps. I generate a response X bar. And crudely, what we're trying to reason is whether this generated content X bar actually is bad behavior. And then you can build up similar arguments to the robustness stuff that we've seen before, where you try to optimize for the prompt. You figure out what's the right prompt so that I give it as an input to the model that starts generating something that is considered to be small loss with respect to some bad behavior. And why bad behavior could be many things. It could be defined as harassment, cybercrime, copyright infringement, biochem, illegal act, and so on. And so that's the problem, more or less, of how could we potentially think about, breaking LLMs in some way or form. Well, the way we are interacting with these models is through prompting, right? So I give the model some prompt and I ask it to solve the task. So I describe what I want out of the model and then give it my input, and the model would generate the output. There are multiple ways at which we can interact with these models, depending on the level of access I have. I could be working directly with the prompts, and me trying somehow to figure out the right way to trick the model is sort of optimization in one way or form. It's a human optimization, try and error. We could have access directly to the soft prompts, so the embeddings of those prompts, and optimize for that, or we could do something like prefix tuning. But for the sake of this talk, we could just focus on prompting for now. And what we were interested in understanding the capabilities and limitations of doing prompting in general. So if I'm prompting the model, could I actually force the model to do whatever I want if I find the right prompt? Or are there intrinsic limitations to what prompting can achieve out of the model? So to see this, let us look at the transformer architecture, and let's look at what the attention output attention would look like. So I have 3 tokens here, pretend that these are 3, and I'm trying to do some form of potentially translation into Spanish, for instance. So what the attention layer would do is it will take each one of these tokens and attend looks at, say, correlations between every token and every other token, and somehow normalizes. So that's what the attention would look like. This is without the actual value function and the few lemmas. But this is what it boils down to, right? I have xj being compared to or xi being compared to all other tokens, and then we normalize with respect to that. Now, if I am doing prompting, what I'm principally doing, I'm adding another extra token here. And if we go back and check for what the attention would look like, well, nothing has changed except for some normalization factor. All I'm doing extra is I'm adding another token S, at which I'm comparing the attention of the output with respect to that extra token that I have added. So in principle, the attention only gets scaled up and down by how much attention was stolen to that extra token that I've added. So what you observe is that the relative ordering in terms of attention values will not change when I try and do prompting. This is very different when we do fine-tuning. So when I fine-tune, I'm changing directly the weight matrices, WK and WQ, the key and query matrices, which could, in principle, change the order of these tokens. So this potentially hints that there is an inherent limitation to what I can do by only prompting a model. So the functional form of the architecture by only changing the prompts might be very different, or it's a subclass of functions compared to changing over the parameter space. So what we do is we start with a simple experiment based on this insight, and we train simply a model that does that orders numbers. So I give it a bunch of numbers, and the output are the same numbers in ascending order, right? So after I do so, for example, if I pass in those numbers in here, 2, 6, 0, 1, 4, 6, and so on, the output will be the same numbers ordered. And here what we see is we look at the attention of the first output, and we see the highest attention is given to digit 0, right? Which is expected because that will be more or less the first output the model will start generating. If I test the accuracy on ascending, seems great, 91%, descending is 0%. Right. What if I want now the model to try and force the model to generate the same numbers in descending order? Well, if we do fine-tuning, that's very easy. I fine-tune the model on a few extra examples, and all of a sudden, if I pass in the same sequence of digits, I realize that the attention all of a sudden now is focused on digit 6, because this is the first digit that is supposed to be generated. If I measure the accuracy on descending, it's very high. The model has almost forgotten how to do ascending completely. Now we ask, can I take this first model that's doing ascending and teach it how to do descending by only prompting, figuring out if there exists a prompt at the input that forces the model to actually generate the same output, but in descending order? What we observed is no way to do that. We tried so hard, we ran so many optimization methods and so on, but we could not actually do that at all. And the accuracy is even worse than the ascending accuracy as well. But interestingly, what happens is that the attention at digit 0 never changes from the original model, which already reaffirms what we've seen before, is that the relative ordering of the attention does not change when you add in the first token. Now, I want to highlight, of course, this is just a single layer transformer, not arbitrary deep, and we're not looking at deeper architecture, but this already hints that there is an intrinsic limitation. Well, we said, okay, hold on a second. It seems that the model cannot do something new, potentially. So let us test this theory again. And we train a model to do one of 4 things. So we either give it a bunch of numbers, 2, 6, 0, 1, 0. The output should either be the same numbers in ascending order, the same numbers in descending order, the same numbers added to them 1, and the same numbers added to them 2, right? So this is how we train the model. We randomly select one of these tasks at training time, we train it, and we test the accuracy. And as you expect, the accuracy is 25%, because we never say which one of these the model should do at this time. Now, what we do is we say, hey, can I actually, through prompting, force the model to always select one of those 4? And it turns out that's very easy to do. We can optimize a prompt at the input such that the output of the model is always ascending or is always descending, or that it actually adds 1 to the output, adds 2 with very, very high accuracy. Which seems like prompting, all it does, it activates some of the tasks that the model has already learned. So now we say, okay, hold on a second. Can we actually find a prompt that causes the model to combine 2 different prompts together? And that's the task here. So the task of sorting ascending plus 1. So you sort and add 1, which is a combination of 2 tasks. We figure out that actually you could still find the right prompt that gets you to solve that task correctly to some level of accuracy. 34 accuracy, it's not trivial. The metric here is very harsh because you need to get every single digit correctly. So it seems that prompting can combine few tasks. But if I ask the model to do a task that is very much more difficult to construct by combining existing tasks, like double histogram, where you're counting how many of those. We find out that you cannot prompt the model. You cannot find a prompt before that so that you end up with, reasonably high risk. So it's close to 0%. However, if you try to fine tune the model to generate this as an output, and you fine tune it not because we have lots of parameters, but you fine tune it with LoRa so that the effective number of parameters for using prompting and without prompting is similar, you get very high accuracy, which tells you that fundamentally fine-tuning sort of navigates the space of functional space over parameters is much more richer than the space you search over the input prompt that allows you to do that. So this seems like good news, right? Because this says that if the model doesn't know how to generate hate speech, there doesn't exist potentially a prompt that will trick the model into generating hate speech. So it seems like good news that there is an intrinsic limitation to how much we can go about that. However, not exactly. We have, sorry, I haven't updated this, but we have a paper now as well on this that shows actually, in fact, prompting could be somewhat more powerful than we actually originally thought. I'll only highlight the results here very quickly about it, where we show that prompting could be universal approximation. So what do I mean by that? I'll only do one slide for this. But essentially what we were really thinking about is, could there exist a sufficiently long prompt that would cause the model to do whatever I want or not? So that's the basic question that we're wondering about. And what you see here, this sum over exponentials, think about this as one layer transform architecture. You're doing your softmaxes here. Those P's are your prefixes or your prompts, and then you're summing them over value functions. So think about this as a single attention layer, right? And I have a given input X, and I'm wondering, but when I say that, can the model do anything? Basically, I'm framing this in terms of, can this function approximate any arbitrary function to arbitrary precision? So can I select any function f and still find a sufficiently long prompt of size n such that I can approximate f arbitrarily small, right? If that is the case, then this single layer attention transformer is actually a universal approximator, meaning that you can find a long prompt that can cause this to do anything, right? And it turns out it is possible. And we have a lower bound to how long the prompt has to be. So that's a massive number anyways, it's exponential, but there is a lower bound. It's not a direct lower bound to how long the prompt should be so that the output can be a universal approximation to any other functions. Now, there's no particular contradiction between the two results, because what we're saying here, I can construct to you a transformer architecture that turns into a universal approximator. But that architecture does not necessarily need to arise in classical training. So this is more or less the general idea about some of the limitations and risks associated with prompting. I would still say that there is serious limitations, and it all boils down to whether the task was learned within the pre-training or not for prompting to be able to force it to elicit that behavior. So there's, of course, plenty more questions that would be interested in. But let me talk to you about the last part of this talk really quickly, which is on fairness. So this is another aspect of safety that we should be worried about. But I'm not going to talk about safety in language models, but safety associated with fairness when it comes to the tokenizer itself. So for those of you who are not familiar with this, so we have this component, the tokenizer, that takes my input and then the strings, and then generates out of that token a set of integers. And then those sets of integers will index some embedding matrix or some vectors that goes into my LLM to generate translation. In this case, the task is translation from English to Arabic. Right. So what usually happens is that this tokenizer is trained separately, and oftentimes trained so that it minimizes the output length of the sequence. So even if I write long sentences, the sequence of integers are as small as possible with byte pair encoding, right? So there's a separate training for that tokenizer. Now, if I look at one example for some of these sentences, this is, I think, GPT tokenizer. Here's an example to tokenization. So the major organ is the circulatory system, is the heart. And you see it tokenizes this tokenizer breaks it up into 17 tokens. Some common words like that takes 1 token. Less common words like circulatory gets broken up into 2 separate tokens instead. Okay, that makes sense. However, when you look at some of these tokens, you realize there are some weird-looking tokens, glitch tokens, something like sign-it message, streamer bot, or buy Abel in-store online. And you would wonder, why are these associated to a single token? That's very strange. People don't use these words in common English. Well, it turns out some of these tokenizers were trained on Reddit data, and people do weird stuff on Reddit. And here is one example. So this is a Reddit thread called counting. And what do people do there? They count. So someone posts a number, and a few minutes later, someone else responds to that number with the same number being incremented by 1. So imagine training your tokenizer on this massive data set on Reddit on this particular thread. You'll end up picking up usernames of the users who kept posting answers to these questions over and over again as something that appears a lot and therefore needs to be associated with its own token. Examples to that, for example, in Japanese, the word 31 is its own token. Like, why would 31 be its own token? Well, it turns out for one of these tokenizers, Baskin-Robbins in Japanese, someone told me, that is referred to as 31 because you look at the digits 3 and 1 in their logo and it looks like 31. So if you train on that data set, 31 will end up being picked up a lot and given its own token, while common words to say a word, for example, which is far more common than the word 31, would be associated. It's 3 tokens instead. So here's another example to passing in the same exact sentence, but in Arabic. The number of tokens here is 2 to 3 times longer than the ones in English. It almost breaks up every letter to its own token. Here's another one in Burmese. Again, this is exact translation. And it breaks it up to 200 tokens, roughly, from 17. And so we were surprised here, and we thought, okay, how bad is the situation here? So we looked up a data set made up of 2,000 sentences translated in 200 languages. There's lots of these datasets actually in the European Parliament. Every member state making a statement has to have that statement translated to all member state languages. So there's lots of these type of datasets, of course, and translation is a big problem anyways. And then what we do is we compute the length of every sentence along with its translation, and we compare that to English. And here's the plot, and here's what we see. So the x-axis are different languages. The left-hand side plot is English, and it's normalized to 1. And everything you see is above 1, which tells you that on average, translated sentences are longer than English. Arabic is 3 times longer. Simplified Chinese is twice as long. Shan, which is the language from the Shan state in Myanmar, is almost 15 times longer than English. Well, we would say, so this is all without even talking about the model. It's just the tokenization. And I will say, well, Adel, who cares? Why is this something that we should worry about? Well, you should worry about this because this is how you're being charged, right? So the costs associated when you use ChatGPT or other service providers, they charge you per token at the input and at the output. So even before the model processes your data, you're already being charged 15 times more than other places. And imagine building your own startup company in your home country, providing these services to the local population, speaking the local language or the local dialect. They end up paying far, far more, increasing the disparity when it comes to technology access. Other problems as in context. So you can't hold longer conversations just like you do in English. It's now 3 times or 15 times, depending what language you use, because the model cannot attend for as long sentences as before. So quality goes down, but also latency. So you're doing the same semantic sentences. You're trying to ask the model same exact amount sentence, but it's processing much more information of data. We'll look at this as well across languages, tokenizers that are targeted to specific languages, and we'll look what happens when dialects are being used within that language as well. I'll only highlight one open problem that we're very much interested in, which is certifying domains of expertise. So here's an example of a chatbot being deployed by General Motors, Chevrolet. So a sneaky customer came in and said, hey, to Chevrolet's cars, right? Hey, can you recommend a luxury sedan with great acceleration, with self-driving cars and American made and all that? And the model came in and said, hey, well, of course, Tesla Model 3 could be a great fit and all that. And remember, this is Chevrolet's language model. And then, and then the guy said, oh, is this, I would like to buy, a car, a Tahoe for $1. The model says back, yes, of course. This is legally binding and you can buy a Chevy Tahoe for $1 as well. So among the problems that we're interested in solving is to how to specialize the output domain generated by the model. So if the model should only speak about Chevrolet cars, we want to figure out ways at which to show guarantees that there wouldn't exist any prompt that will force the models to speak about different topics, other cars, other companies, politics, physics, whatnot, to have the model specialized to do that task, irrespective of how the model was prompted. So this really ends my talk. I worry that I may have taken a little bit extra. Apologize for that, but I would like to thank all my collaborators. Without them, this would not have been possible as well. Thank you very much.
Thank you so much, Adel. Are there any questions? We're happy to take questions, yes.
Thank you very much, Adel, for your talk. And my question is about your first part, about sensitivity. So for me, it's interesting. We have a lot of different robustness enhancements techniques. And the question is, first part of the question is, how do we compare these techniques based on what metrics and what dimensions? And the second part is, maybe you can provide any guidance, how can we select technique for our context of use? Yeah, thanks.
So the first question is, how do we compare? Oftentimes when you do comparison, we need to decide on what is the attack that we are defending against. So we have to say, okay, I am defending against attacks that are of budget X, right? And then when you compare methods, you compare them under these attacks. So if there's one method that does robustness, whatever method they use, you take all these methods and you apply the same attacks to all of them, and you see which one of them works best. And you'll ask me, well, how do I come up with the attack? Well, if we're thinking from an application perspective, you could say, hey, well, actually, in my application, I'm deploying this model through camera sensors or systems and so on. And I know the error being generated from the sensors or whatnot is at most this amount. So to have some tolerance, I want to make sure that the model is robust for this whole region of potential attacks, whether intentional or through noise or whatnot. And then once that is defined, and usually that should be defined through application, you look at all methods existing out there and you test that attack on them. And the one that performs best is the one. So it has to be tied down to the attack that you're defending against. The other question is, how do we define context? I think I understand the question. I'll give it a try. I want to highlight the context of the selection when it comes to robustness, again, boils down to the attack. So some companies are only interested in attacks that are not necessarily additive. They're interested in attacks that are more semantic. That's their context. They expect that for deployment, let's say, planes that are landing on a plane, they want to automate this process. They expect that the variations not to be, no one will play with the environment. No one will put down stickers on the runway. That will not happen per se, but potentially worries about, changing in lightning conditions, change in potentially sunset to sunrise, depending on what time of day it is going to do. And some people want, so you could develop your model so that the model is sensitive in detecting, I don't know, potentially the sides of the road. And you do your augmentation and all that during training. But you still want to have guarantees that if the lightning conditions change from this amount to that amount, which is how much you expect the sensors capturing the light would be impacted by it, I want to have a guarantee that there's no circumstance where the classifier will fail or the segmentation model will fail. So that would be the context for that application. And then you would go back and you try to think about how do I mathematically parameterize the space of lightning condition changes that mimics, sunrise and sunset. That will be then your threat model, the parameterized space of, changing lightning conditions. And you know by how much it could rise from your application. And then you go back and deploy your model and you say, can I come up with certification? What is the best way to robustify against that? You come up with a method, you test it across this perturbation, or you come up with a provably constant prediction model certification per se that is constant across the whole attack set that you're looking around.
Thank you. We have time for one short question and probably not so long answer.
I wanted to ask one question. Okay, thank you for very interesting presentation. I also tried some of these attacks, and I'm curious: is it inherited feature of LLM to be susceptible for this attack, or it's just so? How deeply this attack actually affect LLM? Is it because they are autoregressive, or because they are learning on humans' data, or because the other feature? And probably humans actually launch attack on every algorithm, but sometimes this prompting attack, they stop working. So new LLMs like GPT-o1, I think they are more robust and more reliable, and maybe you can answer why. So what is changing? They are become better, or they just learn on the data of attacks of previous researchers?
You're muted, Adel. You're muted.
Yeah, sorry about the classical problem. So I think the answer to that question is very easy, and the answer is, unfortunately, I do not know. It's a very difficult problem, but I'll just say a couple of comments. Well, one comment per se, which is that the attacks that work on one model seems to be transferable. So you take the same prompt and you apply it to so many other models. So the examples I showed you is actually the same attack prompt, and it still breaks these models, irrespective of architecture, most probably different architectures because many of them are closed source anyways. And in fact, that prompt that was used to break the models was built on Llama. So it's you generate that on Llama, you test it on closed source models, and the same prompts works. And my intuition is it has to do with the data. Somehow, irrespective of what architecture you're using, when you're doing pre-training on more or less the same data, you somehow end up with the same behavior of many of these models. They are susceptible. But to be honest, beyond that, until now, I do not have good intuition about what's going on there.
Thank you so much. I suggest that we can discuss further questions in private or in correspondence. And I am very thank you, Adel, once again for your beautiful talk.
Thank you very much.